Assalamu alaikum wa rahmatullahi wa barakatuh. Our lesson today to explain a very important test for any imaging system is called modulation transfer function. This test is very important and interesting test because this test enables us to be sure that our imaging machine has the ability to differentiate between two nearest points. So if I did the test for modulation transfer function, that will enable me to judge the machine, to say that machine has the ability to do our scan or not. So let us talk together about modulation transfer function. Modulation transfer function definition. You can see in front of you, this is a quadrubar phantom. This quadrubar phantom is consisted of line pairs. What's the meaning of line pairs? You will find here black lines and white lines. This black line is composed of lead and this white line is composed of plastic. So this line this black one and white is called together line pair. So number of line pairs per centimeters here is around 3.5 line pairs per centimeter. Here the gap is enlarged and number of line pairs per centimeter will be larger. Here you will find number of line pairs per centimeter is decreased. Here you will find that the last square, you will find that number of line pairs per centimeter is more and more. So the efficiency of my machine, of the imaging machine, to differentiate between these line pairs, it's called MTF, modulation transfer function. You will find that MTF value is from 0 to 1. From 0 to 1. 1 represents 100% resolution. 0% resolution. So as you can see for this CT image here, line pairs per centimeter and the gap is decreased, so the number of line pairs become greater. Here the number of line is the gap is decreased more and more, so the number of line pairs become more and more, and so on. So here I will find that the gap in first one is around 1.6 millimeter, second one 1.3 millimeter, third one 1 millimeter, and so on. So this gap reduced, so number of line pairs per centimeter increased. Let us discuss together very important meaning about transferring special domain to frequency domain. Here is our phantom. You can see here line pairs in this one, in this square. Number of line pairs here is per centimeter is greater one. So you can imagine that the repetition of line pairs here is a slow repetition, because number of line pairs is per centimeter is not large number, is small number. So there is the repetition of line pairs here is slow. So this repetition mean frequency. So the frequency, I can represent this line pair by this first one, wave. This wave, slow frequency wave. Second one, Number of line pairs increased per centimeter, so the repetition also is increased, so I can represent this box like this, so the frequency is become faster. Third one, as you can see, number of line pairs increased more and more, so line pairs here increased per centimeter, so the frequency become faster. The last one, the gap is reduced and decreased, and line pairs per centimeter become more and more, become largest one. So if you represent this repetition by this frequency, you will find this fastest frequency, fastest one. So I can say I can represent the line pairs or spatial domain to be, the line pair can represent this line pairs to be frequency domain. Okay, so I can convert from spatial domain to frequency domain. Why you said that, why you explain this definition, you will know now. Now this is my line pairs. This black one is lead and this white one is plastic. Okay, so if I scan quad bar phantom like this one, okay, on gamma camera, I will put a point source away from this quad bar phantom and take an image like this. Here I will get this image, okay, on imaging of quad bar phantoms, and these line pairs, okay, black one is lead, white is plastic, okay, and the spaces line pairs here per centimeter, and the gap here is largest one, decreased more and more. So you will find the efficiency of the machine to differentiate between this line pair, it's called MTF. So I'll get back here again. This lead is the line, black line, and this lead will absorb a lot of radiation, so low amount or low counts of radiation will be transmitted to be detected with gamma camera. So the counts here will be very low, but on the other side you will find the plastic white, the plastic one, which will be high counts. So high counts here in this region and low counts here in this region, you will find this wave like this. Okay, so if I wanted to calculate MTF, I have to calculate the contrast of the image, divided by the contrast of the object in the real. So the contrast of the object is also equal to 1 because it is a real contrast, it is a real value, not dependent on the imaging system. This contrast, the contrast of object, any object has a contrast equal to 1. Okay, but if your imaging system can't differentiate this object from background, this is the problem of your imaging system, not the problem of object. Okay, so this contrast of object, okay, will be equal to 1. Okay, so the contrast of the image will be I maximum minus I minimum divided by I maximum plus I minimum. So I will get the higher counts here minus the minimum counts divided by higher counts plus minimum counts. If the contrast of the image is equal to 1 and the contrast of object equal to 1, so the same, so the MTF value will be 1. It is 100%. But you will not find the contrast of image is equal to 1. It's hard to find this. You will find this in line pairs, in a small number of line pairs per centimeters for small frequency. So small frequency, okay, highest frequency. Small frequency represent small frequency, okay, represent number of line pairs with large gap, but higher frequency represent number of line pairs with small, very small gap. So with this higher frequency, with low frequency, you will find MTF is higher. So with higher frequency, you will get MTF will be lower. So this is the curve of MTF. You'll find on y-axis MTF and on x-axis special frequency, which represent line of pairs per centimeters. Here 0 line pairs per centimeters. Okay, here low number of line pairs per centimeter. You will get MTF is equal to 1. It is the highest value of MTF. So when the line pairs of line pairs per centimeter increase, what happened for MTF? MTF decline, which indicates that the capability of the machine to differentiate between large number of line pairs will decrease. So here at 3.5 millimeter gap, this number represents the gap between line pairs. Here the gap is very large, 3.5. You will find the MTF is equal to 1. Here the gap is reduced. You will find the MTF is decreased. Here 2.5 millimeters, the gap is reduced more and more, so number of line pairs will be increased. If you compare between number of line pairs here and per centimeter and number of line pairs here at 3 millimeter and number of line pairs at 2.5 millimeters, you will find that number of line pairs at 2.5 millimeter is greater 1. So the MTF value will be lowest one here, because the spaces between line pairs are decreased more and more, so MTF will be lower. You can here differentiate between 3 gamma cameras for instance, as an example, or 3 imaging system. You will find that this one here at low frequency mean again, a very large gap between line pairs, and number of line pairs per centimeter is low. So you will find the MTF is high. So and so on. Number of line pairs increase per centimeter, special frequency increase, the same meaning, you will find the curve decline. But here I will find at a certain point, at a certain special frequency, for instance at this point, you will find that at this point MTF value for this imaging system is the lowest one. So this imaging system is the worst one, because the MTF value is around 0.1 for 2 millimeter gap, Okay, this is a quadruple phantom. Okay, if I want to calculate the MTF value practically, what will I do? It's easy to draw ROI like this on every line pair to get a value of mean value and standard deviation. What that mean? If the gap between line pairs large, so you will get a variation in the Hounsfield unit or in the counts inside this row. Inside the region of interest you will get a variation, so the standard deviation value will be high. But if the gap between line pairs is very low, the gap is small, if the gap is small between line pairs, so you can find no variation, no greater variation, no large variation between the Hounsfield unit or the counts inside the region of interest. Again, I will draw the region of interest, okay, inside the line pairs, inside the group of line pairs, okay. So I will get, as you can see, mean value and standard deviation value, okay. Here 1, 2, 3, okay. 1 mean value is 67, 2 66, 3 69. Standard deviation here is 30.30 here, because there is a gap between line pairs, so there is variation in Hounsfield unit, so we will find standard deviation is highest one. Here 2, the gap is decreased, so the variation also will be decreased, so you will find standard deviation is around 21. Here 3, you will find standard deviation 15, lowest value, so and so on, okay. I will get this value of standard deviation to represent the resolution of the system, again. Here this is my phantom image, okay. Here I will find that first group of line pairs 3.2 line pairs per centimeters, second one 3.95. You find that number of line pairs per centimeter increased because the gap is decreased, so number of line pairs will be increased. Here the gap is larger, so number of line pairs per centimeter will be decreased 1.6, here 1.9, 2.4, here 1, 0.6. So now I have the values of number of line pairs per centimeter for all groups of line pairs in my CT image, okay. So I will draw the region of interest and I will get the standard deviation like this for each one of line pairs per centimeter. First one is 0.6. This one I will draw the row, I will draw the region of interest inside this group, which is 0.6 line pairs per centimeter, and I will get standard deviation. Another one for 1 line pair per centimeter, I will get 57, and so on. You will make a relation between line pairs per centimeter, which is the special frequency, and standard deviation. After that, I will do normalization for the standard deviation value. So normalization mean I will divide 60.5 on the same value 60.5 to be 1, which is 100%, and divide every number of standard deviation on the maximum number on the 60.5 to get a certain value, okay. After that, I will make a relation between line pairs per centimeters and MTF percentage. Here the highest one is 100, okay, which represented here 60.5 divided by 60.5 will get 1 times 100 will get equal to 100%, and you will find the decline in the curve, okay, with increasing line pairs per centimeter, okay. This is the theoretical base of MTF, modulation transfer function. If we want to calculate the modulation transfer function practically, you need to scan phantom for CT. You want to scan the phantom for CT to get an image for line pairs, and using ImageJ program, I will open it. Hang up. Okay, it's open. I will found here file, open. Okay, I saved my my image. QC applications. MTF, first one. Okay. Yes. This is the image of phantom and this line bears, and I have the manual of cat phantom, and well, number of line bears per centimeter. Okay, so this image using 120 kV is an axial image using 180 milliampere, rotation time 1 second. Okay, you can get it, and it's preferable to use 1.25 or lowest slice thickness. Okay, so I will draw Roy here using square or rectangle. Okay, press analyze, measure. Okay, you will get mean, standard deviation. Okay, I need this one only, so I can results, set measurements. Okay, standard deviation for first one. I will draw okay, make sure that the ROI inside the group of line pairs, not outside. Okay, measure. Okay, analyze, measure. You will get that the standard deviation value decreased. Analyze, measure. Yes, analyze, measure. I can using control and scroll to move to be sure. Analyze, measure. Yes, again control and scroll. Okay, here. Okay, analyze, measure. Here. Analyze, measure. Analyze, measure. Here. Analyze, measure. Analyze, measure. Okay, I'm sorry, I repeat this again. You can do something, it will be easy. You can rotate the image, transform, rotate 15 degree. I'm sorry, again, image, transform, rotate the image 15 degree, image, transform, rotate the image 15 degree, image, transform, rotate 15 degree. Okay, so you can do this like this, it will be easy. Okay, again, analyze, measure. So I will do something, I will do from the biggest one. I need analyze, measure. Okay, I'm sorry, again, analyze, measure. Okay, analyze, measure. Okay, analyze, measure. Analyze, measure. Analyze, measure. Analyze, measure. Analyze, measure. This is a manual procedure. Okay, for calculating MTF. You can find software in your CT machine to calculate MTF automatically. You will find option for MTF calculation from point spread function converted to line spread function, and after that will be converted to MTF, modulation transfer function. Now each one 1 2 3 4 okay till 11 has standard deviation value. I want to draw my curve, file, save as. Okay, I'll save it here, results, save. Okay, okay, or you can do something other, it will be easier. This is your result. Okay, copy, analyze, tools, again analyze, tools, curve fitting, control V. Okay, and change this value. Here you will write number of line pairs 0.6, 1, 1.6, and so on. Okay, in order to change 0.6 number of line pairs, 2, 1, 1.6, 1.9, 1, 1.6, 1.9, 2.4, 3.2, 2.4, 3.2, 3.95, 3.9, okay, 5, 6.4, 11.499 11.3. Okay, I forget something to do normalization. I want to do normalization for this standard deviation value. Okay, so I'll get this copy again and open Excel sheet. Okay, Control V, you will find the values. Control X, Control V, line pairs per centimeters, and this one standard deviation, and this one after normalization. Normalization. Okay. You will do something while the same value like this one. Okay, and get second value divided by the first one, get third value divided by the first one. Okay, okay, we'll change it. P2, P2, okay, P2, P2, okay, or you can put dollar sign, okay, like this. Not working. Okay, so I have the values for line pairs of centimeter and normalization. Okay, I can delete this easily, no need. Sorry. With line pairs of centimeter, Control C, Control V, and normalization value, Control V, which MTF value. Okay, now I can draw, insert, scatter. Okay, I will switch. Special frequency and MTF. I'm sorry, something wrong. Again, Control X, Control V. Okay, insert, scatter. Okay, add trend line. Exponential, I think. Okay, close. Okay, now you can calculate MTF value, modulation transfer function manually. Okay, now I can get the line pairs per the MTF value for my machine to check if the machine has the ability to differentiate between two nearest point. Now if I want to check that at 0.1 here, okay, I will find that at this value, okay, the line pairs per centimeters will be around 7.5 line pairs per centimeters. Okay, now you can check and you can calculate MTF manually, and you can check your machine. You can check your machine monthly about the MTF. Okay, it's easy to do. Okay, only you need phantom for line pairs per centimeter or quadrubar phantom. You can do the same technique for gamma camera using quadrubar phantom, but here you don't have large number of line pairs, but only four line pairs, four gaps only for quadrubar. Okay, I wish to understand how to calculate MTF and what is the meaning of modulation transfer function. Thank you. See you later. Assalamu alaikum wa rahmatullahi wa barakatuh.